Okay, let's just dive right into this explainer. If you're a postgraduate researcher gearing up for your thesis or a major paper, you already know methodology isn't just some section you have to write to tick a box. No, it is literally the engine of your entire project. Today, we're doing a masterclass on designing a rigorous, defendable quantitative study from the ground up, so that engine runs perfectly and captures objective data that stands up to the absolute highest academic scrutiny.
We'll be following a step-by-step roadmap today. We've got 5 critical stages. 1, the foundation. 2, the blueprint. 3, the participants. 4, the instruments. And finally, 5, the proof.
All right, stage 1, the foundation, variables and hypotheses.
As a researcher, you've really got to think of quantitative research design as your systematic blueprint for objective numerical measurement. It's built on the philosophy that reality is objective, right? It can be measured. You aren't just kind of casually observing things. You are predetermining exactly what data is going to be collected, from whom, and exactly how it's going to be analyzed to test your theories.
To build that blueprint, you've got to lock in your variables. Specifically, you need to draw a hard line between the independent variable, which is the cause you manipulate, and the dependent variable, which is the outcome that's affected. The independent variable is basically your active ingredient. It's what you, the researcher, introduce. The dependent variable is what you measure to see if that active ingredient actually did anything at all.
But wait, you've also got to account for extraneous variables. These are those uncontrolled factors that can just quietly sneak in and totally skew your hard-earned data if you aren't careful. For instance, say you're testing a new teaching method. Well, a student's baseline motivation, or even whether the library coffee machine was broken that morning, those are extraneous variables. If you don't control for them, you have no idea if your independent variable actually caused the change, or if you just had a highly caffeinated group of students.
Let's look at a running example. Think about how the independent variable of, say, a teaching method flows directly into the dependent variable of academic performance. You manipulate how the students are taught, maybe using digital platforms versus traditional lectures, and then you measure the resulting shift in their academic performance, usually through test scores.
So, the crucial thing here is that we test this relationship using hypotheses. We contrast the null hypothesis, which states there is zero relationship, against the alternative hypothesis, which is the relationship we actually hope to prove. Now, as a researcher, you're actually testing the null. You're hunting for enough statistical evidence to confidently reject the idea that your teaching method had absolutely no effect. Reject the null, and you get to embrace your alternative hypothesis.
Moving on to stage 2, the blueprint, selecting a research design.
Now that your variables and hypotheses are locked, you have to pick the actual methodological blueprint. This is your primary fork in the road. Experimental designs, focusing on manipulation and control, versus non-experimental designs, which are all about observation and description. If you want to definitively prove cause and effect, you've got to go experimental. But if you just want to describe a current phenomenon, look at correlations, or survey a population without interfering, you'll choose a non-experimental route.
If you do go the experimental route, a basic, true experimental structure contrasts an experimental group that gets the treatment against a strict control group that doesn't. Notice the symmetry there. Both groups take a post-test, but only one gets the active treatment. Plus, in a true experiment, you'd randomly assign participants to those groups, just to wash out all those pesky extraneous variables we talked about earlier.
All right, stage 3, the participants, sampling methods. The design is locked. Now, who exactly are you testing? Since you rarely have the time or money to test an entire population, you have to pick a sample. And you have to critically choose between probability sampling, where every single member has a known chance of being selected, and non-probability sampling, where that chance is unequal. Probability sampling is absolutely the gold standard for generalizing your results because it completely removes researcher bias. But look, in the real world of social science or education, it's often logistically impossible, which naturally pushes us toward non-probability alternatives. Your specific method could range from simple random or stratified sampling for probability to convenience or purpose of sampling if you just don't have full access to the population. Stratified sampling is amazing if you need to ensure specific subgroups, like different grade levels, are proportionally represented. On the flip side, convenience sampling, which is literally just testing the class you currently teach, is super common. You just have to heavily acknowledge its limitations in your final proposal.
Which brings us to stage 4, the instruments, validity and reliability.
You've got your participants, but how do you know your questionnaires or tests are actually capturing the truth? A study is literally only as good as its tools. And this is a classic mix-up, but your data collection tools have 2 absolute non-negotiables:
reliability and validity. Think of a dartboard. Reliability means your darts are highly consistent, hitting the exact same spot over and over. Validity means those darts are actually hitting the bullseye, measuring what they intend to measure. If your survey questions confuse half your participants, your instrument might be reliable at producing bad data, but it completely lacks validity.
Finally, stage 5, the proof, data analysis.
You've collected the numbers. Now you have to make them speak. When you first look at that raw data, you're going to use descriptive statistics, things like mean, median, and standard deviation. This is your summary, your high-level overview. It tells you the average performance of your groups and how spread out their scores were. But keep in mind, descriptive stats only describe the exact sample you tested. They don't prove your hypothesis on a grander scale.
To confidently prove your alternative hypothesis and actually generalize your findings to the wider world, you have to rely on inferential statistics, like a t-test or an ANOVA. And remember, your earlier design choices dictate your math here. If your blueprint had one experimental group and one control group, two distinct groups, you run a t-test. If you had 3 different teaching methods to compare, you run an ANOVA. This is the moment of truth where you calculate that crucial p-value to finally reject your null hypothesis.
So, as postgraduate researchers, you are now equipped with the master blueprint. From variables and design to samples, instruments, and that final analysis, the structure is entirely in your hands. Thinking about your own field of study, what breakthrough will your data reveal? Thanks for joining me on this explainer, and happy researching.